Welcome again in Adash tutorial video. In this one we will explain and describe the ACMT measurement method. The ACMT enables to measure very long time signals on high frequency range 25 kHz. Mostly it is used on low speed machines for detection of roller bearing faults. Imagine the roller bearing. Here is the failure. When the ball is passing, then the shock appears in the signal. The time length of this transient event is very short. If the speed is low, for example 60 rpm, then there is a long time interval between individual shocks. The time interval between shocks is 1 second in this example. If we want to have at least 10 events in the signal, then we have to measure 10 seconds. Now we will zoom one shock. You can see that the shock has something like natural frequency, and it is really the natural frequency of some mechanical structure. It can be the bearing body, it can be the bearing house. The real shock signal will contain more natural frequencies inside. You can see the time length t of one period. We can get the corresponding frequency f equal 1 divided by that t period. This frequency f is usually between 5 and 20 kHz. It means that the length of shock is usually only several milliseconds. If we want to see all details of this shock, then we must use the high frequency range up to 25 kHz. It means the sampling frequency will be 65 kHz. If we need to get time signal 1 minute long, then we get 4 million samples. When one sample needs 4 bytes, then it is 16 megabytes for one measurement. It is a huge number and most analyzers cannot do it. The Adash analyzers have such long signals available, but if we would be saving such a huge signals to the memory, then we will have to work with gigabytes. You can argue that I should use lower sampling frequency, but it does not work. We would have long time between samples and we lose the shape of the signal. Additionally, the anti-aliasing low-pass filtering will remove high frequencies, but we need them. The natural frequencies of shocks are in high range. The Adash analyzers have the ACMT measurement available. It is the compression of the time signal. The measurement is made with high sampling frequency 65 kHz and then it is compressed to low frequency, typically 1 kHz. The compression has unique properties. It keeps the shape of the signal. It means all high frequency shocks remain visible. We have the record which contains shocks. It is rough signal captured on the machine earlier. You can hear it. Firstly, I will measure the normal time signal 8 seconds long. The 500,000 time samples will be measured. All shocks are clearly displayed. Now I add the ACMT as next measurement. I will measure again 8 seconds, but the sampling frequency is only 1 kHz. I will get only 8,000 samples, and you can again see all shocks in both graphs. Now I apply zoom to both signals. Here you can see the difference between time signal and compressed ACMT. The shape is not the same. The losing of the shape is the price of compression we must pay. Analyzers of other producers can have measurement method which could seem similar to ACMT, but it is not true. Such methods only works as capturing of peak value in short interval. That works with absolute values of samples and the result looks like this. It does not look like a time signal. The ACMT always looks like time signal and you can apply next methods to it. For example, you can apply the demodulated spectrum for bearing fault frequencies analysis. The ACMT has one important property which is not available in any other analyzer. All other analyzers with their capturing procedures can work only with transient events like shocks. The ACMT can work with all types of signals. You can use it, for example, for compression of pure sine wave signal. This is the example with 50 Hz pure sine. The ACMT can be used in two different ways. I can set the RMS compression or the true peak compression. If I choose the RMS, then the RMS of ACMT signal is equal to the RMS of original time signal. If I choose the peak, then the true peak value of ACMT is equal to the true peak of original signal. I work rather with RMS values because it enables good trending in time. The RMS is much more stable than true peak. It is clear when I select RMS compression, then the peaks in signal will be lower than peaks in original signal. It is the mathematic rule. The ACMT is a very powerful tool for all measurements where we need long signal, typically on slow speed machines as I mentioned on the beginning. Thank you for watching.